We're going to be talking today about logical replication protocol versions. So I'm Kevin. I'm currently a software engineer at Clickhouse. Clickhouse being an open source analytical database that's like really popular and pretty increasing popularity in the community. Before I started working at Clickhouse, I was working at a startup called PODB. The startup was designing an ETL tool from Postgres to other destinations. So our only source was Postgres, and we moved data from Postgres to Kafka, BigQuery, ClickHouse, and other destinations. And we use logical replication for this purpose. And because of our focus on logical replication and rock solid performance for Postgres data movement, we were acquired by ClickHouse last year to make the data movement experience from from Postgres to ClickHouse as rock solid as possible. That's why we were acquired, and that's what I've been working on in ClickHouse ever since. PODB is still an open source project. You can look at it at the top right. There's a QR code for that, and we are still working actively on PODB. So let's go over today's agenda briefly. So I'll give a quick introduction and to all the Postgres replication methods overall. Then we'll go into logical replication, which is what we're talking about today. Then we'll talk a bit about logical replication. Then we'll talk about protocol version 1, 2, 3, and 4, along with some demos in the middle and some comparisons. And then we'll wrap up the talk. And I'll also be stopping periodically to for if anyone has questions. So if you have questions when I stop, you can ask them. So let's go over what Postgres replication methods briefly. So why would you want to move data from Postgres to Postgres? There are many reasons for this. In case you have a high availability setup, like in case you have like RDS, multiple Postgres setup, or like a read replica in RDS or GCP, or you want to make backups of your data on Postgres, you would want to move data from Postgres to a different Postgres instance for that purpose. And all the current replication methods that Postgres has all center around the concept of a wall or a write ahead log. The write ahead log is a pretty common data structure in databases. It's basically a way that Postgres ensures transactional durability. So basically, every time some change is made to a Postgres table, it's stored in the wall. And even if a change is uncommitted, these changes are still stored in the write ahead log. And this is what is used by all the replication methods in Postgres. The first method, which is the oldest one, is something that's called log shipping, which is basically a way that entire wall files are moved from server to server. So in case there's a wall file on the source, we just move the entire file to the destination, and that's how the replication of data is done. We just move the files over. And a slightly newer method is called streaming replication. This method basically takes individual wall records, so bits of write ahead log, and moves them to the destination over like a connection between the source and target. So it's a slightly more advanced version of log shipping. Both these methods, the write ahead log, they process them. They don't really process the wall, they just send bits of write ahead log from source to destination. So they're pretty reliable methods. And if you use like an RDS read replica or a HA setup in like any cloud provider, they'll end up using either log shipping or streaming replication for achieving that. But one downside of the write ahead log is that it's a global entity. Like every change in any database would be in the wall, so you can't really filter out what I want to move. I can only move everything to my target Postgres database. So the newest method that Postgres has is something that's called logical replication. It was introduced in Postgres 10, so around 8 years ago now. It's a pretty flexible method of replication compared to the previous ones. You can move data and do online migrations, and also you can upgrade, move data between versions of Postgres. So if you have Postgres 16 and 17, you can move data across the versions, which is not easy with the other methods. And this uses the streaming replication protocol. So this protocol is used, but instead of sending the raw wall records, it processes the records. We'll get into what the processing is later. And the wall records are processed to map to transactions before they're sent to the destination of the subscriber. Because of this processing step, you can filter out changes at the table level. So if I don't want to move one table to the destination, I can do that. I can filter on the column level. I can even filter individual rows in a table out if needed via logical replication. It's a pretty powerful feature like that. And this is also exposed to users directly via SQL commands. So I can create logical application via SQL statements basically. The two entities here are called a publication and a subscription. A publication is basically like a filter. You can assume it basically selects what you want to replicate. So if I want to move tables T1 and T2, I would do create publication with T1 and T2 in it to select that. A subscription on the subscriber, so subscription is on the destination, attaches to the publication and replicates data that the publication wants to replicate. The subscriptions are a wrapper around the underlying thing that's called a logical replication slot, and this logical replication slot is what actually does the actual CDC or change data capture. And while Postgres uses subscriptions like PeerDB and other ETL tools will directly use slots for moving data from Postgres to Clickhouse or anything else. Before we move on, are there any questions? I think not. Okay, cool. Thank you. So let's see how logical application works briefly. So it's not a simple thing to take wall records and make them into sort of like a different format. So there's a lot of infrastructure that is needed for wall records to turn into like a sequence of messages that can fully represent a transaction. The first step here is something called reordering. So basically what happens is if a transaction takes a long time, the wall or write ahead log multiple write ahead log files can contain the same transaction. You can have it in like 10 different files because the transaction took that much time. Each wall file is a fixed size. And there's also a thing where it could be interleaved with other transactions. If I have like 3 transactions happening at once, because of that I have 3 transactions worth of changes in the same wall file. So I need to take these wall files and sort of reorder them to make it represent the sequence of a transaction's changes. And this requires memory to reassemble, and large transactions can even like require spilling to disk to reorder it. So it's a pretty hefty operation for larger transactions. After the reordering is done, the next step is what's called an output plugin. So the reorder buffer passes changes into an output plugin via like a callback. So basically C library that you can write and you can get the data from the reorder buffer. The most common one is what's called PG output. That is a standard output plugin that Postgres ships. The other one's called wall to JSON or decoder buffs, and there are many plugins, but the most common one is PG output. And the aim of an output plugin is to take a wall record, which are a pretty low level representation of things, to make it into like a standardized format that like anything can use. So PeerDB, Debezium, all these ETL tools are able to understand logical application output because it's written like a standardized format. Subscriber basically keeps sending messages to the output plugin to the slot to indicate that I have read these changes. So we get 2 inserts. Then after that, the subscriber tells key I have gotten these 2 inserts, and after that, the slot can sort of advance and remove older walls. So it doesn't have to retain the older files. After the subscriber acknowledges that it has done changes up till this point, it can advance and discard older wall. So this is like a pictorial representation of the same. So on the left side we have 2 Postgres tables T1 and T2, and they're having transactions on them, changes being done to the tables. Let's assume there's a publication on these 2 tables. Then after that, the transactions that are happening are somehow sent to 2 different wall files because they're very big transactions. So you can see that the green transaction and the blue transaction are in 2 different wall files. They're also interleaved with each other because they're happening at the same time. So what you have to do is we first start the reorder buffer. The reorder buffer takes the wall files and then puts them, makes them into a sequence of changes. So it takes all the begin inserts and makes them into a single chain for that transaction. So if you see transaction ID 27137 has all its changes in one area, and the other transaction is separated. The separation step is what reorder buffer does. After that, the output plugin takes these changes that reorder buffer makes and translates them into protocol messages. These messages have different meanings, they're different types, we'll get into that later. But the core concept is the raw changes from the write ahead log are sent to the output plugin, which converts them into sort of a standardized format. Finally, these changes are sent to the logical application slot. The slot sends these changes to the standby. The standby sends some acknowledgement back saying I have read until this point. And after that, we can advance the slot to read newer changes. That's how logical replication ends up panning out. So we can look at some of the sample messages as well. So this is a Go struct version of them. These are not how they actually look in Postgres, but just like to represent them. So you can see at the top left corner, there's like a message type. So in PG output, which is the protocol, the plugin we're talking about, PG output has many message types. You can see some of them in the top left corner, like you can see begin message and so on. And let's go over some messages briefly. So a begin message just indicates that a transaction has started, a transaction IDs in the begin message. You can see the XIDs, the transaction ID. Relation message is an interesting one because it's not mapping to a SQL statement. A begin message is basically representing a table. So a begin message, relation message represents a table. So it has a relation ID, which is the table's OID. It has information about the columns. It has a number of columns, types of columns. All that is stored as relation message. And this information is supposed to be used by subscribers to decode insert messages. So insert messages are containing changes for one row. So if I insert one row into Postgres, that translates into one insert message. This one insert message needs a relation message for that same table. So you can see that the relation ID is also present in the insert message. These two are used together to decode what the insert message contains and sort of apply that change onto the destination. We'll get into what the messages do exactly, but this is kind of how they're laid out in memory. So this is like the basis of the talk. So now if you go to the Postgres docs on the bottom, you can see that there is this little field called proto version. And this says that, you know, protocol version, currently versions 1, 2, 3, 4 are supported. But even though it talks about like what 2, 3 and 4 does, you don't really know how they're implemented underneath. It's just this like blurb. But here we are talking about, you know, what these versions do. This is kind of the basis of the talk. So are there any other questions regarding?
About the reorder buffer.
Yes.
Is that a memory structure that's common to all processes, or is specific to the wall sender or the decoder?
The reorder buffer would be part of the wall sender.
So that's a local memory structure, right?
It's like local to the process, yes.
And if there is a transaction that spans 10 hours, what would an impact of that be on the reorder buffer? Would logical decoding workmap have a role to play?
Yeah, so logical decoding workmap has a role to play this. I'll get to that later. But the idea is if a transaction has a lot of changes, it will spill from reorder buffer to disk for the reordering. The reordering will still happen, but it will happen on disk instead of on memory because of the constraint from logical decoding workmap.
And there is no way that we can change the size of the reorder buffer, right?
The reorder buffer is limited by logical decoding workmap. So if I increase logical decoding workmap, it increases the reorder buffer size essentially. Yeah. Any other questions?
Is there anything that we can control the time spent on the ordering, or is it only memory spaces?
It's memory space. Increasing memory space. So logical decoding workmap is a parameter. Increasing that is kind of the only way. You, in case you would want faster disk as well, but kind of the only way is to increase a parameter and also have less chunky transactions. You don't want a transaction that's really big, that's really difficult to reorder. So you want to have smaller transactions. That is kind of the way you would fix an issue if your reorder buffer is a limit. We'll get to questions later, but let's move on. So let's get into protocol version 1, the oldest protocol version, which has been there since the very beginning. So in this protocol version, transactions are only sent on the slot once they have been committed. Regardless of the size of the transaction, they're only sent once they're committed. And the way the protocol pans out is we first get a begin message. The begin message is what I shown earlier. The begin message contains a transaction ID, also known as an XID. After we get the begin message, we get relation messages for one or more tables based on how many tables are in the transaction. Then after that, we can get n number of inserts, updates, deletes. And the point here is that regardless of the number of rows that a statement affects, if a single statement touches 10 million rows, we will get 10 million changes for each row updated or deleted or whatever. And because the changes are known to be committed already to disk, we can apply them immediately. So if you get changes, you can immediately put them on your destination. You don't have to wait for anything. And then we get a commit message to signal the end of a transaction. After the transaction ends, we will never see the same XID again. So that's how V1 pans out. So let's get into a quick demo, which is a live demo. So that's going to be interesting. So I've written a little Go program to sort of connect to Postgres and sort of show how logical application works. It's a program that I have written in Go. It's not Postgres. So on the left side, let's start reading a slot that I've already created beforehand. And I'm selecting protocol version 1 for this. So it's connected to the slot, is reading stuff. Now on the right side, we'll start generating transactions. So let's generate a transaction of 100,000 rows, small transaction. So it's insert a transaction. Now on the left side, you can see that I have done, you can see a begin message has come. You can see that after that you got a relation message. The inserts are not shown because the inserts will be a lot of data output. But you can see that we got a begin message, a relation message, and a commit message, and then a transaction is done. And you can see it had read 100,000 rows. The key point here is now I can make a transaction with 10 times the rows, but only after the transaction finishes, we will see the transaction read on the left side. So now it's reading a transaction and it's done. So the point here is regardless of the size of a transaction, you will only see it after commit. And now on the other hand, if I start a transaction and I stop it, the transaction never appears because it's a rollback transaction which is not sent on the protocol. That is how version 1 pans out. So let's go back to the talk. Yeah, okay. So again, just to explain things a bit clearer, let's go for a simple transaction. So the begin statement that I run on the top, this is a to insert transaction. The begin message maps, the begin statement maps to a begin message. Then even though we haven't really done anything, we get a relation message for the table that is being inserted into. After that, we see an insert message for the first row and insert message for the second row. After that, we see the commit mapping to a commit message, which has a commit LSN. And after this, we see that you have read a transaction with 2 rows in it. So this is how it would look for V1. This is kind of how we are presenting it. It looks different for Postgres subscribers, but this is how I'm printing it to be understandable. So are there any questions regarding V1?
How will Postgres know that the order in which the commit is happening? Because as I understand, it's only happening in the order of commit, but LSN is what are recorded in the wall. Right? The LSN numbers are what is recorded in the wall in a sequential order. So how would Postgres know that this is the transaction to be decoded at this point in time? Is there a marker to know that the order of commit?
So the wall, my understanding is the wall has a commit record. I think the first commit record it sees, it decodes that transaction. Does that make sense? So the commit record also has a wall position, and based on the first commit record, it sees, it decodes that transaction in version 1. I hope. I think I'll go back, see the begin message and sort of map it out. Basically, even commit messages have like wall records, which should help it go back and figure the transaction out, is my understanding. Anyone else?
So there are multiple begin transactions. So how does it map? Does it show nested structure, or it will be like you mentioned this reordering, and then it will show single begin message, and then transactions, and then another relation insert, and then receives.
Where are the multiple begins? I'm not understanding. Sorry.
There are multiple transactions are happening.
Yeah. So you'll get a begin message with. So the transaction has a transaction ID. You'll get a begin message with that transaction ID. You'll see that begin message with transaction ID 2804 whatever. If you start under begin, it'll have a different transaction ID. Does that answer your question?
Yeah. I was like wondering what about reordering. So when we do reordering, does it have different, or it is still the transaction segment separate?
The transaction is separated by reorder buffer. The transaction is reordered one at a time by reorder buffer. Like it doesn't reorder multiple transactions at once, is my understanding.
Can we shut off the reordering?
You can shut it off by stopping replication. I mean, then how would the logical application work is the question.
No, my question is if there is an application job which has some inserts, which have some flags,
Yeah.
which has to run in an order.
Yeah.
What is the reordering? Might screw that job.
The reordering won't screw it. The point of reordering is basically if there's other transactions in the middle. Suppose a different application runs a transaction for some reason, it is to remove that transaction changes. So it'll always be in the same order as the transaction. It's just if there's other stuff in the middle, the reorder buffer removes that and makes it like a single sequence. There's no changing of order by reorder buffer. It's just other stuff is removed and it's all condensed into one sequence. Okay, so let's move on. So protocol version 2. This is a pretty interesting and big change from protocol version 1. This is introduced in 2021, so like 4 years ago, and this supports streaming of in-progress transactions. Now, an in-progress transaction is not something that's not been committed yet; it's in progress, and this is a setting that you have to opt in while starting replication. It's not on by default. You have to turn on replication, and then this starts working. So in version 2, there's a lot of different messages happening. You have a stream start message. The stream start message is what is instead of a begin message. The first time we see a stream start message for a given transaction ID, we initialize this transaction in setup state for the transaction. After a stream start message, we get relation message followed by inserts as version 1. The difference here is the format of the message has been changed so that each individual insert now contains a transaction ID as well. Before, the insert message did not contain a transaction ID. Here they do. We'll get into why that's needed later, but the format has been changed. After that, we can get a stream stop message. So stream stop message is the end of the transaction stream. So the transaction is done for now. The transaction is not committed, or we don't know anything about the transaction, but the transaction changes have stopped streaming. Now, to decide the transaction's fate, you have either stream commit message or stream abort message. Stream commit message is for commit and other one for rollback. This can come at any point after the first stream starts stop cycle. So you can get 1,000 different streams, maybe 4 days later you see the stream commit. You have to hold the changes in memory or disk for 4 days until you get a stream commit message. And several transactions can be in the middle of streaming. So because of that, you need to track all these transactions separately. In version 1, you get begin, transaction done. So you will do one at a time. In version 2, you can get streams of multiple transactions at the same time. So you need to hold multiple transactions state at the same time. But with version 2, we can still receive smaller transactions that are already committed. You only send larger transactions over the streaming protocol. So you get smaller transactions as part of the earlier protocol. That makes sense. So another demo time. So let's go here. So let's stop replication and restart it with protocol 2, and let's do the same thing we did last time. Yeah. So we're inserting 100,000 rows again. So you can see that here, even though transaction is still happening, we got a stream start with some inserts and a stream stop. So you can see that the first stream start, read some rows. So after a stream stop, you can see that it read 6,000 rows roughly. You can see current count 6K. Then after a second stream stop, we get some more rows, some more rows, some more rows. So instead of getting 100,000 rows at once, it sends in batches around 6K rows. And this means that the transaction is being sent much faster to the subscriber because it's being sent as it's happening. And now if you take a much larger transaction, it's doing the starting and stopping, but now if I stop the transaction, it says stream abort message, transaction is aborted. So the changes were coming even though the transaction is eventually going to be aborted, but despite that, changes were sent to the destination. But now after the transaction was cut off, we get a stream abort message from Postgres saying that the transaction is no longer valid, destroy the transaction, do not do anything with it. So this is how version 2 pans out. Let's go back to the presentation. Yep, okay. So let's again go through a smaller transaction to show version 2 in more detail. So I've enabled a debug flag here for it to be more obvious. Like I have explained, smaller transactions shouldn't be streamed. They'll always be done by version 1, but just for the sake of clarity, I've enabled this debug flag. So we do a begin maps to a stream start message this time. Then after that, we get a stream start with a single insert message in the middle, and then you get a stream stop. Then you get another stream start, another message in the middle, then another stream stop. Then finally, the commit maps to a stream commit message, and that finalizes the transaction. In the last line, you can see that we read 2 rows and there were 2 streams, one stream for each row. That is kind of how version 2 pans out. Are there any questions regarding version 2?
If the long running transaction spans multiple wall size, previously we saw the logical decoding workflow can be a bottleneck for that. But in this case, it's also the subscriber which will now have to hold on to most many transactions before it receives a commit or an abort.
Correct. I'll get into how that works later, but that's a good point. But currently Postgres mostly puts it to disk. It's not a memory bound thing.
But still there will be a performance implication
there will be, but again, in generally, we don't want long running transactions for logical replication, but in version 2, it's on a subscriber, like you said, to hold the changes for a long time, but it's sent to disk. It's not in memory, just like logical decoding workflow. It's a
logical folder which gets to hold all this stuff.
I'm not sure which folder it is, but it's on disk. Yeah. Okay. So let's move on to some challenges in implementing protocol version 2. Protocol version 2 is really cool. It can make some transactions a lot faster to apply, but there's a lot of challenges in implementing version 2 that stems from the fact that this is a transaction that's in progress being sent. You need to take care of it very carefully. So the first thing is the streaming frequency is not random. It's dependent on a setting called logical decoding workmem, which controls the maximum memory that the reordered buffer process uses. This max memory is, I think, by default 64 MB, something like that. But the point is, how it works is, in case a transaction is about to hit this limit, Postgres decides that this transaction is too big, let's stream it instead. So Postgres streams on the basis of this parameter. This parameter is set to a lower value. We will get the changes being sent more frequently. The transaction to a very high value, Postgres decides that there's no need to send this transaction because you can handle it without streaming it. So because of that reason, the streaming frequency is dependent, and you should not have a very low setting for logical decoding workflow, because that can affect throughput of streaming because it happens too frequently. Second thing is, like the question pointed out, we need to wait for commit or rollback to apply the transaction. You have to wait for as long as it takes for the transaction to apply, and they need to be staged somewhere. They can't be put on a destination directly. Postgres in version 2 opts for spooling the changes to a file. That's where the transaction changes are put. That's what it does currently. The third sort of nuance is that Postgres supports transactional DDL. I can do a create table or alter table in a transaction, and if the transaction rolls back, the table is not there anymore. Because of this nuance, the relation message I see in a transaction that's being streamed is only applicable to that transaction. If I do an alter table add column to in a transaction, the transaction is the only entity that knows this column exists. The other transactions don't know this column exists yet. So I need to store this relation message on a per transaction basis for protocol version 2. The last issue is regarding sub-transactions. Sub-transactions in Postgres are the syntax is something called save point and then roll back to save point. Now the issue with sub-transactions is they can abort independently. So I can have a top level transaction that's going on. I create a save point and then I can roll back to the same point. So some of the transaction is aborted, but not all of it. So we need to keep track of sub-transactions as well in version 2, because there is a possibility of sub-transactions aborting independently of the top level transaction, and that means you have to sort of take care of sub-transaction changes being discarded and not the top level transaction. Thankfully, only top level transactions can commit, so I can only do commit at the top level, but I can abort at the sub-transaction level. So because of that, I need to map changes as well as abort to sub-transactions instead of top level transactions, if that makes sense. Are there any questions for this a bit? Yeah.
Not really related to protocols, but recovery conflicts which happen in the vault play, specifically in the stack diagrams.
Sometimes, yeah.
Handled in logical replication.
Recovery conflict, so it's on a read replica. Like I'm replicating from a standby.
Priority has changed, let's say, the row.
Yeah.
Actually, the replica is particularly to get the recovery conflict.
So then the slot invalidates. Like if case that happens, slot invalidation is there. The expectation is the person running the database has to take care of it. They can use this hot standby feedback. That's a setting that you can enable on the standby to ensure that the Postgres doesn't remove the older version of the row. There's a setting called hot standby feedback.
Are there drawbacks of that?
There are drawbacks of that, but the point is, because you're replicating from a standby, you need to either enable HS feedback, or you need to be careful of recovery conflicts not happening. It's not something that an ETL tool or an external thing can control, if that makes sense. It's not something that we can directly control, and we can have slot invalidations if the recovery conflicts happen. It can happen to some customers based on the workload. So you can compare the performance of protocol versions 1 and 2. This is wait, sorry, this is a wrong slide. Yep, sorry, this is the right slide. So all graphs. So this is from a blog post that I've written on this topic as well. So all graphs here show 2 concurrent transactions happening. Each transaction inserts 25 million rows for a total of 50 million rows in 2 transactions. Now what you can see here is pretty interesting. So you can see the slot size growth. Now what is slot size is the amount of retained write ahead log by the slot. I have, like I explained earlier, to sort of send changes to the subscriber or standby, you need to have retained wall for decoding the changes. Now if a transaction is going on for a long time, you retain a lot of changes for the transaction to be decoded. So you can see that as a transaction is it's a large transaction, as the transaction is like progressing, you end up hitting what, 8 GB of wall roughly. And this is just a consequence of how logical replication works. Unless a transaction is decoded, you have to keep the wall that the transaction needs available. So protocol version 2 doesn't really help with that. What it helps with is the time for it to drop. So you can see that in version 1, because after the, so the red line is where the transaction commits and the green line is when the transaction starts. Sorry for not mentioning that. But the point here is, for version 2, you can see that immediately after the commit and the red line, the slot size can drop, because between the green and red lines, the slot was being read by the streaming transaction mode. In version 1, you can't do that. Version 1 only sends transactions after commit time. Because of this, you can only send, you have to wait a long time, like a few minutes in this case, but could be hours for larger transactions, for the slot size to be at that high level before a transaction is fully read, and then the transaction can drop, the slot can drop. So this doesn't help with slot growth, it helps with dropping the slot faster for larger transactions. Sorry, I have to go back. Yeah. So this is another graph. This shows the records read over time. It's just for like information. You can see that in version 1, the rows read are at the very bottom, like 0 rows read until a transaction commits in a red line. Then you can see transaction rows are being read really quickly. In version 2, the lots more spikier. You can see that rows are being read so on during a transaction, and then immediately the transaction commit, the rows read goes to 0 because the transaction has committed immediately after the transaction has been read. So before we get into version 3 and 4, how many people here know what a prepare transaction in Postgres is, or like two-phase commit? Few people. That's why the slide is there. So what is two-phase commit? So two-phase commit is pretty interesting. Two-phase commit is a sort of a distributed algorithm that involves coordinators and participants. That's a terminology for two-phase commit. So what two-phase commit lets you do is lets you execute a transaction across multiple distinct participants. So if I have like a MongoDB database and a Postgres database, I can run a transaction across these two if the transactions support two-phase commit protocol. So what happens in two-phase commit is, suppose I need to make changes on a MongoDB database and a Postgres database. I as a coordinator tell MongoDB to prepare for commit. This preparation step does all this work necessary to commit, but doesn't actually do the work. So it, for example, it writes files, it takes all the locks needed, all that stuff. But the point of this preparation step is that commit should not fail post preparation. That's the entire logic of this. So after MongoDB is made to prepare, Postgres also does its preparation. Now, if Postgres fails to prepare, if Postgres has some error, doesn't get the locks, or something happens, Postgres, as the coordinator, detects this failure and then can ask MongoDB to roll back because Postgres has failed to prepare. Vice versa, if MongoDB fails and Postgres succeeds, Postgres can be asked to roll back. Now, after everyone is done preparing, everyone has done the work needed to prepare, the coordinator can ask everyone to do the commit. This commit is kind of like a fake commit because all the commit work is done earlier. It's just that the coordinator knows that all databases or message queues or whatever is involved can safely do the work now. So it does the committing afterwards. So that is the entire idea of two-phase commit. Postgres supports two-phase commit via prepare transactions. Prepare transactions are kind of like a niche feature of Postgres, and they are disabled by default. By default, you can't do prepare transactions. After you enable them, you can run prepare transaction as a statement. And this does most of the work that commit needs. It writes wall, it takes locks, it does everything needed, but it doesn't actually make the changes visible. So if I do select star later, the transaction is prepared, but the changes are not visible yet. I still need to wait for a commit or rollback decision on a prepared transaction to be done. Now, unfortunately, when a transaction is in the prepared state, it resembles a long-running transaction in a lot of ways. So it holds locks open and can block vacuums. So the understanding is you don't want to hold a prepared transaction open for long, because if it is held open for long, you can have issues with vacuuming and long running long held locks because of a prepared transaction, which is why they're disabled by default as well. So just to like sort of SQL syntax of prepared transaction, you can see that I started a transaction, I inserted a single row, and then I did prepare transaction with a certain name called the GID of the transaction. After the transaction is prepared, it's done. You can't interact with the transaction anymore. It's fully done. But if I query the system, the catalog table called PG prepared Zacts, I can see this transaction exists. It's prepared, and now even if Postgres crashes or something happens with Postgres after preparation, nothing will happen to the transaction. Transaction is completely safe. But you can see that the transaction even after preparation still holds locks. So you can see that the locks are still held after the preparation state as well. And now to finish the job, I do commit prepared with the GID from earlier, and that finishes the transaction. Now the row is visible. This is how prepared transactions look in Postgres. Are there any questions?
Not only blocks the button, right? Also blocks all the VM operations.
It depends. If it takes a row level lock, it wouldn't, right? Yeah, so it depends on the operation being done. I think if it takes like an exclusive lock on a table, that would be a problem. But if it takes a row level lock, I think other rows can still have changes being done to them.
Does it change the isolation level at that time, the prepared transaction, or it will still be repeatable?
I think you can adjust the isolation level when the transaction is started. I don't think the prepared transaction has any effect on it, but I could be wrong. I'll get back to you later. I am not sure about the isolation level and prepared transactions. So protocol version 3, as you might have guessed, talks about prepared transactions, introduced in Postgres version 15, so 3 years ago. This supports prepared transactions, but the important caveat here is it supports prepared transactions only if you put a parameter while creating the slot. This is not something that you can do while the replication is started. This is a one-time setting at the slot creation time. Now before this change, you would still get prepared transactions. They wouldn't like be invisible. What would happen is you would only show up if they were committed, or you would have a stream transaction show up as a stream commit or stream abort. So basically they would appear as normal transactions. You would not see the prepared aspect of them. You would just see that the committed or rolled back. Now in prepared transactions, what do you have? You have no new fancier message types. You have begin prepare. Begin prepare is the analog to a begin message. So if we get a begin prepare message, that means we are reading a transaction that's prepared, and a prepared transaction ends with a prepare message, not a commit message, a prepare message. Now even after the prepare, the transaction is still not done. We still have to wait for a commit prepared or a rollback prepared. So we start with a begin prepare, we read changes, insert, updates, delete, whatever. Then you see a prepare message, and then we wait for a commit prepared or rollback prepared. That is what decides the fate of a transaction, similar to how stream transactions work. If a prepared transaction was streamed earlier, it's slightly different. Now instead of getting a stream commit message, we get a stream prepare message. So the stream commit equivalent is stream prepare. And then afterwards the stream prepare, we either get a commit prepared or rollback prepared. So in both cases, it's a two-phase operation. We have to see a prepare message or a stream prepare message followed by a commit prepared or rollback prepared message. So that sort of exposes a version 3 the prepared transaction semantics to the logical replication protocol. Let's quickly do version 4 as well. So version 4 is the newest version. It's introduced 2 years ago. This supports parallel apply of large stream transactions, and this is again a start replication time setting. So now what happens in version 4 is instead of the changes being spooled to a file, which is what happened in version 2, we have something called a parallel apply worker. It's a new process that is spun up by Postgres, and the changes for the transaction are sent to the parallel apply worker via shared memory is the implementation. And the parallel apply worker applies them on the destination. This is and the parallel apply worker is assigned till transaction commit. Until the transaction commits, the parallel apply worker stays, and this helps with applying large transactions faster, because instead of spooling, we can just apply them. Now parallel apply is not always used, because there can be cases where if this parallel transaction, there can be some data inconsistencies, or there could be deadlocks in some cases. So because of this, some transactions still use a spooling approach from earlier. And protocol version 4 doesn't really change the messages much. It's not mean changes to the messages itself, but what happens is Postgres has written a lot of code in subscriber, like the subscription side code to handle transactions, and also the logic to spin up a parallel worker and like what a parallel worker does. So most of the changes for protocol version 4 are not in the protocol. There's a couple of changes, but very minor ones. But the major thing with protocol version 4 is the subscriber has changed a lot of code to make parallel apply possible. Let's get into conclusion as well. So over the past 4 years, like in the past 4 years, we've had 3 new versions. We've had 1 new version for Postgres versions 14, 15, and 16. Over the past 4 years, we've seen 3 new versions. So basically, a lot of changes have happened in the past 3 years in the logical replication protocol by the Postgres team. And these have led to improved performance for replicating some workloads and also better support for some features like prepare transactions. For users of Postgres subscription, so if I just do a create subscription and then connect to the publisher, I don't really need to think much. I just enable the settings I need and then everything works because Postgres has done the stuff for us in the subscriber side. But for ETL tools such as PADB, we need to sort of work to implement V2 independently. Postgres has done its work, but because we want to move stuff from Postgres to something else, we need to do the work to support these newer versions. So if you want to support versions 2, 3, and 4, we have to put the work ourselves, which is what we are actively working on, implementing protocol version 2. So we can stream transactions a lot faster, larger transactions. And they need to be done carefully because it's pretty intricate stuff. And again, we hope that the Postgres team continues to invest in logical replication. It's a great feature that helps make a lot of stuff possible, data movement tools possible, and makes it more performant while keeping it easy to use for users. And that wraps up my talk. Thanks a lot. Do we have time for questions or next talk? Yeah. Is there any questions?
When you're dealing with logical replication, how does pause work and how long do you pause running subscribe?
Ideally, never. You would keep the subscriber running constantly. So one thing that PADB internally does is we don't want to lose the replication connection. We want to keep it active as long as we can, unless the customer decides to pause it, obviously. But ideally, never is the answer. But even if you pause it, as long as the changes don't accumulate too much, you should be fine. Like you can pause it, but if you have a lot of changes happening on the source, you can have like the wall spike to hundreds of GB in like a few hours. So it depends on your workload, but the ideal answer is never pause the subscription.